I have a question, if it's okay to ask.
Sure, go ahead.
Okay. I'm stuck on, I think this is 2B. I want to make sure it's right. Yeah, 2B. Like I see how the function's like reacting. I guess is how I see it, or how it like
Hmm.
grows. But I don't know how you would put it into a series. Like I understand like the top portion is +4 each time, or +4 from the last term. And
Okay.
then the bottom is going to be +3 from the last term. But I wasn't too sure how you could write that. Like it kind of confused me on like how you do it, if that
Okay.
makes sense. Like I
Good.
understand how it's growing, I just don't know how you could put that. Like it's not n+2 or times that, and it like confused me, and I don't see how you could do it.
Good. So let's see what you got. Because writing it out and kind of understanding how it grows is the first step, and then maybe we can try to pick out the pieces and sort of arrive at some sort of series for this. And some of these you can do, and some of these you can't. I don't know if we can actually come up with a
Yeah.
closed form expression for this. Sorry, this one was 11.
Yeah, to be honest, I was a bit confused on like just this one in general, just finding the patterns. Like that can be really tough. And I still don't like I managed to find it, but I still don't fully understand like is there like a method to like finding like the patterns in these like sequences or
They're both 14 on the last one.
14, 14. Yeah, sorry.
No, you're fine.
Um, when we when we have sequences written out, really what you want to do is rely on your skills back to when we were talking about sequences from the get-go. When we built up linear sequences, geometric sequences are good frameworks, and then just general patterns of functions. Of course, if you see, natural log of 2, natural log of 2 times natural log of 6, well, then you can throw in the functions and stuff in there as well. Really, the framework from all of these is geometric and linear patterns, then within bigger patterns, if that makes sense. So we've kind of got patterns within patterns growing, because it looks something like a factorial, kind of, right? Because we're multiplying consecutive terms, but it's also not a factorial because we're not multiplying uh, by the next consecutive term every time. We're multiplying by a different increment of terms. So this is what Ryan was saying. He was saying, I see the pattern. He was saying it, the terms we grow each time are going to grow linearly. We're adding 4 to get the next one on the numerator, and then we're adding 3 every time to get the next one on the denominator. So the general format for a lot of these, you guys aren't going to have a great formula for. This gets into what's called product notation, just as how we can have this sigma represent a sum of a bunch of terms. If we have a product of a bunch of terms, we can write it with what's called a capital pi in sort of the same sense. But that's a little bit beyond this course. You guys might get to it in higher math once you get it to maybe differential equations. For now, we kind of just want you to understand the basics and be able to describe what's going on with this sequence. So let's do one more term. So what's the next term going to be? So this is what's written in the problem.
I think 18 and 17.
Yes, we have the product of all the previous terms. But then the numerator is going to grow. The next one's going to be 18. And the denominator is only going to grow by times 3. So then we're going to add a bunch of terms. And so let's practice. We're gonna multiply however many terms that are coming next. Here, did I write one wrong? Yeah, this one should be 14, sorry. Times 17. So this was our first one. This was our second term, our third, our fourth, our fifth. What's the nth term gonna be here? What is the thing we should multiply the numerator by in the nth term? Let's come up with a formula for that.
Couldn't you pull out a 2 in each term? So then you get 2 times 3, then 2 times 5, 2 times 7, and then 2 times 9. So then that means it's constantly being multiplied by 2. So it's 2 times n plus something else.
That's good. So we can use that for sure as well. Here, let's come up with this sequence. Let's just look at the sequence, the sequence of products. So this will actually be useful because sometimes you can factor out some exponential terms and then reduce it down to a factorial and then do some nice simplifications. Sometimes you can't though. We'll see how it works out. So when I was mentioning earlier, we have like sequences within sequences, patterns within patterns, right? We have this multiplication pattern in the sense that it's growing, but really all we're doing is multiplying each sequence by a new term and then keeping all of the old terms there. So it might be helpful to do a little side work of just considering what's this sequence: 2, 6, 10, and then 14, 18. What would a closed form expression of this sequence look like? This will help us fill in what should this nth term be. First suggestion, Ryan said, was to maybe we can pull out a factor of 2. So 2 times 1, 2 times 3, 2 times 5, 2 times 7, 2 times 9. That can help, but now we are also we want a formula now for a new pattern of, well, multiplying by 2 every time is easy. This other pattern we have going is 1, 3, 5, 7, 9. So how do I describe this pattern?
Wouldn't it be n minus 1? Because then, not n minus 1. I think it might just be, ooh. I think I just made this worse.
No, it's actually, I mean, it's easier. It's all the odd numbers, yeah. This is something I wish we could have had time to emphasize a little bit more. I'm kind of glad it's coming up in office hours, and I wish more students were seeing this. Because understanding sequences of even and odd terms is quite pivotal, especially if you're in computer science. It comes up on occasion whenever you're doing lists and matrices where maybe you want all the even ones, maybe you want all the odd terms. So Ali wrote in chat 2n minus 1. That will work. You just got to be careful of where you're starting as. So either 2n minus 1 will work or 2n plus 1. Which one do we want to use? Either one. Just depends on the starting value. I guess since they don't actually list a sequence, all of these start at n equals 1. So let's do 2n minus 1. And so here, this is our n equals 1 term. So if we plug in n equals 1 into this formula, we get 1, n equals 2, n equals 3, and then it goes up. And of course, this is our nth term. So then, in other words, this sequence here, we could describe as 2 times 2 n minus 1. And let's keep it factored. If we wanted to, we could write it as 4n minus 2. But factoring out that 2, sometimes it's helpful. And it often can be with some of these factorial-like growth that's going on. And so we can fill that in with our series now. It's going to be 2 times 2n minus 1. So again, check that. That's our n equals 1, n equals 2, n equals 3. What about the denominator? What's that one going to be?
Well, I noticed you could technically go backwards and do -3, but then that might mess up where you start.
It could still work. Where are you getting the 3 from?
So I was kind of like noticing like 17 minus 3 is 14, then 14 to 11 is -3. So I was trying to see
Yeah.
if you can go, instead of going left, you can go right using that idea, but
So let's take a look at this. I guess maybe we can expand this out if we want to look a little deeper into it. 4n minus 1. If I wrote y equals 4x minus 1, what type of equation is that? Right? It's just a linear equation. So this is our linear sequences. It means that this 4 is our slope, meaning every increment we are increasing by 4. So that's what we originally noticed, adding 4, adding 4, adding 4 to get these consecutive products.
wouldn't it be 4n minus 2 and not 4n minus 1?
2. Yeah.
Okay, because it was like, if you distribute the 2, it should be -2.
Right. Yeah. So here, what are we doing? We're adding 3 every time to get that next term. So if we have this sequence of 5, 8, 11, 14, 17.
Couldn't it be similar to 2n minus 1, but your n would have to be technically 3 for it to start at 5?
Your slope is going to be 3. And then if n starts at 1, let's write it as 3n plus b. What should b be? So if n equals 1, we should get 5.
2 would work, actually.
Exactly like lines. We know the slope from consecutive terms. You can find the intercept that you need just by picking a point. Here, since we're starting at 1, we have to check n equals 1 matches with the n equals 1 term. So a couple things. I do want to talk about this kind of factorial growth. Sometimes it is helpful to factor out these 2s. So because we could factor out a 2 from everything in the numerator, sometimes it's helpful. In this case, it's not going to be. And we'll see why. So we know that our nth term is going to be given by 2 times 6 times 10 times 14 times 18. And then the last term is going to be a product of 2 times 2n minus 1. And in the denominator, we've got 5 times 8 times 11 times 14 times 17. And then the last term, 3n plus 2. We could try to factor out all 2's in the numerator. How would that look? Then I would have a 2 times 1 times 2 times 3 times 2 times 5. When it would go all the way up 2 times 2 to the n minus 1, 2n minus 1, which we could simplify as 2 to the n times 1 times 3 times 5 times 7 times but the result, not a factorial. Just as a side note, sometimes it's kind of nice when there's no shift, when there's not like a minus one. If you have something like let's do 3 times 6 times 9 times 12 times 15 times 3n. In this case, if I factor out a 3 from everything, I'll have a 3 times 3 times 3. So it's 3 times 1 times 3 times 2, 3 times 3, 3 times 4. We can simplify this expression by writing it as 3 to the n times what's going to be left, 1 times 2 times 3 times 4. In other words, it's 3 to the n times n factorial. This is a sneaky way. Sometimes you see problems. Sometimes factorials are hidden within problems, or even though it's not directly a factorial, if you're clever with your factoring, you can see a factorial come out. And then you can do factorial algebra. So if this was like in a numerator, you could cancel it with other factorials in the denominator and do some simplification. Unfortunately, with the way this series is working out, we are left with 1 times 3 times 5, which is, again, it looks like a factorial, but not quite. It's very factorial-like in behavior. So it just means we're going to have to keep it written as it is and work out our algebra a little bit differently. So let's go ahead and keep this as a 4. The other thing you want to make sure to look at is the rate of growth of the term. What is happening after, what is it, n equals 4? So after n equals 4, how do the numerator and denominators compare?
The denominator is larger than the numerator. Or
Uh,
I think vice versa, my bad.
yeah. Numerator is going to be larger than the denominator. And that's always going to be true. So starting here, all of these terms is bigger than 1.
Can you just take the limit of the function 4n minus 2 divided by 3n plus 2 and prove it? Or I mean, you could do ratio test too.
Yeah. So you could do a ratio test on this guy. I mean, it'd be hard because again, you'd have a product, but you're getting closer. The hard is what's going on with the limit of individual terms, but we also have to remember that we have to take into account the product of all the previous terms.
Oh, you can't just ignore them.
Well, the product of terms, so this whole expression is our sequence of individual terms. This is our an. So if we compute the limit as n goes to infinity of 4n minus 2 over 3n plus 2, what's that limit?
4/3.
And then how do we want to use this information is the question.
It's not convergent because it's greater than 1. So then it would all have to be divergent because it's not going to go to a value of 0 at all.
Yeah, you could argue that. Why is it not going to go to a value of 0?
Because like notice above, if the terms keep growing, the numerator is going to grow faster than the denominator, and if you take the limit of it, you get a ratio of 4/3, which is greater than 1 and not less than 1. So that would imply that it's going to be divergent, and it won't ever converge to a single value.
You got to be careful. I'm not sure if you're fully using this limit right and taking into account this product of terms. So you're saying some right things. I'm just not sure if the arguments are solid the way you're really describing it.
True.
So because it's a product of consecutive terms, so a better way to think about it would be to say something like, we know that the limit as n goes to infinity of the next multiple in our sequence is 4/3. And what we noticed was, moreover, that for n bigger than or equal to 5, that 4n minus 2 over 3n plus 2 is bigger than 1.
So could you say with like the argument that anything below n is less than 5, or you could I guess if you say less than 5, then the sequence would technically be convergent, but anything past the value of 5, or if n's greater than 5, then the series would be divergent. Could you say that, or is that something you can't or shouldn't say?
Nah, you can't really say something like that, because any finite value is convergent, and we can't say we just sum up 5 terms and then it converges, because of course we can sum up 10 terms and it'll still converge. The point is that if I keep summing up beyond 5 and keep going out to infinity, that the terms are growing, and moreover we want to compare them to some sort of geometric series. So if this is bigger than 1, this implies then let's write an, which is 2 times 6 times 10 times 14. We can add in our fifth term here. Over 5 times 8 times 11 times 14 times 17 times. We know that each of these terms, 18 over 17, whatever the next one is, whatever the next one is, each of those are bigger than 1. So we could say it's bigger than 2 times 6 times 10 times 14. And this is, of course, for n bigger than 5, bigger or equal to 5. Meaning, what's now going to happen as I take my limit as n goes to infinity of an? It's going to have to be bigger than this term. If every single term in the sequence of individual terms beyond 5 is bigger than this, it'll never get below that. Which means the limit of the sequence, we could actually show that the limit is going to go to infinity, or argue along the lines that it should go to infinity. Simply because we're taking a product of terms. We are multiplying again and again by a number that is bigger than 1. So we could show that the sequence of individual terms goes to infinity, or it is enough to show that the limit of the sequence of individual terms is bounded below, and it's strictly bigger than 0. So by the divergence test, now the series will diverge.
So do I have to, well, not have to, but do I basically just like reason through all that when like writing it down, and then that would is that how you would prove it's divergent? Is by going through like each, I don't know if you say step, but I guess reasoning is a better way to put it.
You want to make arguments and at least explain that the sequence of individual terms won't go to 0, and explain why. The easiest way is essentially you kind of arrived at the fact that the numerator is growing faster than the denominator. And since we are taking consecutive products, eventually every term like this 18 over 17 is bigger than 1. And then the next term is going to be 22 over 20, bigger than 1. So every time I add another term in the sequence, I am multiplying the previous term by a number bigger than 1. You could, if you want, come up with a recursive sequence for it.
Would the ratio test be a false? Well, I don't know if it'd be false. I'd have to mess around with it to figure it out.
You could use the ratio test if you come up with a recursion. So why does this recursion work?
Because an is basically the sum of the 2 times 6 times 10 times 14 is abbreviated as a variable. And then if you do, yeah, then you would just do an plus 1. The an's would cancel out, so it's just a of 1. So it'd just be, I guess, one version of that long ratio. And then, oh wait, I'm just overthinking this now.
So recursive thinking is actually, it's a better way to think about it, really, for this problem. Is it's just that sometimes it's harder for students to recognize a recursion. Especially in a sequence where every time we have a new term in the sequence, it's the old term of the sequence times something new.
That's what
previous term times something new.
Yeah, that's what messed me up, was trying to figure out how I can get or write as a series to get like the previous term.
Yeah, writing something like that
like
as a closed form is pretty hard. as we kind of saw, we couldn't come up with a nice closed form. We could come up with some niceties in terms of figuring out the sequence of multiples, which are in some sense needed for coming up with a recursion. Like we notice that we're multiplying the numerator every time by 4n minus 2. We're multiplying the denominator every time by 3n plus 2, and of course keeping all the previous terms. So anytime we kind of like keep all the previous terms and then do another mathematical operation, whether it's adding something or multiplying by something to all the previous terms, recursions work very well. And now in this case, as you were saying, we could do a ratio test defined by the
an
recursion.
plus 1. Oh, sorry.
4n minus 2 over 3n plus 2. And now, nicely enough, with a recursive formula, the an's are going to cancel. And we, of course, want the limit as n goes to infinity. And now, as you were looking at earlier, if we just look at the limit of these guys, that limit is 4/3. And the heart of it is that now we're using it in a ratio test, which before I was trying to get you to see the geometric property that we are multiplying by something bigger than 1, which is, again, the heart of the ratio test as well.
I don't know. I see it more of the ratio test than the divergence test, to be honest.
This way's a lot quicker. If you understand where the recursion comes from and can demonstrate that this is the correct recursion, it's a lot quicker, a lot more nice and concise.
But the recursion's basically just saying from like the given like values they give you up to, is it 18 or 14 they give it up to?
I think they give you 14.
14. So you basically just go, you just basically put that as a variable. So an's your variable for that. And then anything past like the given values, that's the, I guess the sequences that you, or the series you developed, the 4n and then 3n, that's past the given variables. So then you just do that times an and it makes sense.
Yeah, exactly. We found the sequence of multiples in the numerator, sequence of multiples in the denominator. And that's what we're just multiplying by the next index times this quotient of linear sequences.
Well, that makes a lot more sense. So I appreciate that because that problem stumped me and I felt dumb, but I was just over analyzing it. I was trying to make it into a series, but that ain't happening. So thank you.
Mm-hmm.
Oh, I have a question on 2D. So I ended up trying to use the ratio test to compute that one, and I ended up getting stuck computing the limit. So I simplified it as far as I could, and I got like pi times k plus 2 to the k, and like nothing cancels out. So I don't know.
Ratio test is going to be hard with that guy. Ratio tests are hard. Whenever you have n to the n, we saw this in lecture a little bit. I think I had one example where I had an n to the n, and then we tried to do a ratio test. You can do it. It's fairly hard, though. Easier way to do it might be the root test.
Oh, I could see. I guess you could do the root test for this one.
Yeah, since you have something like some quantity all raised to the k in the numerator, and then quantity in the denominator is k to the k times k. So there's just one extra factor of k, but still that k to the k, it's going to work nicely with the root test.
Wait, so I'm a bit confused on how the k plus 1 would simplify.
Yeah, it's a little weird. What's your numerator?
So when I simplify this, hold on. Would it just be k times root k as your denominator?
K times root k.
I
Not
think
quite.
I think the ratio test would have worked.
It would. You can do ratio tests for these. You just got to
'Cause
be very careful with the arguments.
Because
Yeah.
I got it to work, and the way it did is if you pull out the k's or to the exponents of k's and put them on the outside, the k plus 1 and the k plus 2, both of those k's cancel out, and the plus 1 would cancel out, but the 2 would cancel out the 1, so technically you just have it to the power of 1. Unless that's not at all correct.
It'd just be k in the denominator.
Yeah, so that
Close.
is,
Did you get it, Ryan, or no?
yeah, I had it, it's k to the power of k plus 1 divided by k to the power of k plus 2. The k's cancel out, and the 1 would cancel out, or the 2 would cancel one of the ones, so then you just have k to the power of 1.
It should not cancel that nicely, I don't think. We can do both ways. So
Can we? Because now I'm not too sure about my reasoning.
when I take the numerator, let's work at this kth root first. So let's do the root test and see why it's maybe a little easier. Numerator is easy since we have this whole quantity raised to the k. That simplifies. Now this guy, remember we have exponent raised to an exponent, so you multiply. So it's k plus 1 all over k in that exponent, which you can simplify. It's going to look a little weird because it's going to be k to the 1 plus 1 over k in that exponent. So in some sense, you can kind of think of it as factoring out that one power of k. K to the k raised to the 1 over k is just k, that k to the 1. Then we also have this k to the 1 over k term.
Okay.
And now you got to remember how to compute this limit.
Wouldn't the
Okay.
1 over k just go to 0? So then you just
Yeah.
have k. Okay. And it's just basically pi times 1.
Well,
Not quite. Never mind.
yeah, you got to be careful. The k to the k is, again, hard to work with. We'll have to do a L'Hopital's rule and do a fancy L'Hopital's rule, even with this guy. Fancy derivatives with something like that.
Couldn't you just split the k's in the denominator? So it would be like k multiplied by k to the power of 1 over k.
Yep. If you think that helps. Problem is if we check your infinity for k to the 1 over k, it gives you infinity to the 0, which is an indeterminate form. Here
Right.
it's a little nicer because here it's infinity to the 1 plus 0. So infinity to the 1, still infinity.
Right,
So
right.
here, if I plug in the limit, we get infinity over infinity. Then you can do a L'Hopital's rule. And careful with this derivative here.
Wait, the 1 over x wouldn't just go to 0?
Yeah, in the exponent. That's why it's the limit is going to be infinity to the 1 plus 0.
Couldn't you pull out the pi? So it's just x plus 1 divided by x to the power 1 plus. Okay.
Yep.
And if you just do L'Hopital's, it would just be 1 over 1. Ah.
I guess you might be able to find a way to get around L'Hopital's rule for that.
Yeah, because wouldn't it be on the bottom? Wouldn't it just be just k, and then you just multiply everything 1 by k? 1 over k.
Multiply by...
Yeah, because then you have k plus 1 over k.
You could try to do something like that. Careful with the k plus 1. So you could write it as k over k to the 1 plus 1 over k plus 1 over k to the 1 plus 1 over k. So now this term's going to go to 0. What's happening with this guy?
Doesn't that just...
Wouldn't that just be 1?
Yeah.
Why?
Because it's they're both to the power of 1, because the 1 plus 1 over k, the 1 over k is technically 0, so it's just k divided by k, which is just 1. And then on the one on the right, it's 1 divided by k, so it's 1 divided by infinity, which would be 0. So you just have pi times 1.
You got to be careful with the sequence. You got to apply the limit to all of those terms at the same time. And so what we're seeing in this first term is going to be 1 over k to the 1 over k, right? As Ali was mentioning, we could factor this k to the 1 plus 1 over k like this, which is now a little bit helpful, because if we write that as k times k to the 1 over k, the two powers of k are going to cancel, and we're simply left with this. However, what's this limit? And I forgot the pi there. Oh, no, I did. I got the pi. So this one We already explained it goes to 0, right? It'll be infinity to the 1 plus 0. So infinity to the 1, that's fine. That's an infinity. So 1 over infinity is a 0. This limit, I mean, it's going to be 1, but why? Your reasoning behind why it's 1 isn't quite correct. At least I believe that limit is 1.
Oh, I have a question on 4B. I'm a bit confused on what it's asking because isn't Cn just a constant?
Yep.
So wouldn't that just
Cn is, well, Cn is your sequence of constants, your sequence of coefficients.
okay? So would that, I guess that would just be yes then. I don't like, it's a constant, so it obviously converges. Is that all I really need to explain?
Nah, well, what do you mean by it's a constant? It's not the same term. If it were a constant every single time, it would diverge. It's a sequence of constants. So the constants are changing. It's the sequence of coefficients.
Wait, I'm still confused.
Okay, so in other words, what happens if I plug in an x value of 4?
Well, if I plug in an x value, wouldn't it just be 1 to the n, and then that would just be 1?
Yep, but you'd still have all those CNs that you got to add up.
Mm-hmm.
So another way to phrase B is, does the power series converge at x equals 4?
Yes.
And why can you say that?
Because you're just left with the C.
Well, why do those converge? I can give you a counter example if you want.
Okay.
Yeah, so you can take Cn like 1 over n. Consider like a natural log. If Cn is 1 over n, the radius of convergence might be something different than that's listed in the problem, but there's still going to be a non-zero radius of convergence. There's going to be x values for which it'll converge. But if x is 4, then we're just left with a sum of CNs, which is something like 1 over n. And so it'll actually diverge.
Oh, okay. So I guess, does it depend on the number then?
It depends on the rate of growth of the CNs, or the rate of decay. which we don't know. We kind of have to abstractly intuit what is this rate of growth of CNs, the rate of decay, I should say, of CNs based on the information that we're given.
So I guess it wouldn't always converge. It could diverge as well. We just don't know.
Well, let's try to apply some reasoning. Are we done with this one with 2D?
Yeah.
Okay.
Wouldn't CN, if CN's by itself, that would imply that the x value, since it's x minus 3 to the power of n, your x would have to be 4, so then you get CN by itself. Because if you write it backwards, it would be CN parentheses 4 minus 3 parentheses to the power of n, and 1 to the power of n is just 1 multiple times. So then that's why you get CN by itself.
Yep.
But then since 4 is outside the ratio, it would have to diverge. Unless I did the, that's my question after Ash is done about how to do the, I don't know if it's a table or what, but I'm confused on the ratio, I guess is what it is.
So I know that at this point we converge. At this point, we also converge. What can I say about what's going on in between those numbers?
I feel like those numbers would also converge.
Yeah, right. This is by our radius of convergence. 3 is our center. So we know that the radius of convergence, here, let's write it here. The radius is bigger or equal to 4. The radius could be exactly 4, and 7 could be the largest number where we get convergence. Or it could maybe converge even for 8 or 9, or some decimals in between there. We know at least by 10, it's going to diverge. So we know that the radius of convergence is at least 4, but it's got to be less than 7. So on like A, B, and C, or sorry, 1, 2, and 3 on part A, at x equals 11, what's going to happen?
It's going to diverge.
Yep. So diverge, we are outside of the radius. And then x equals 5. Converge.
I have a quick question.
Here. Yeah.
The 4R and 7, is that because you took or you subtracted the 3 from it? So then would it be 4R minus 3, 7?
That 7 came from here. 10 minus 3.
Okay, so you just don't put the 3. Okay.
That's the distance, right? I know that if I go 7 units away from the center, we're going to diverge.
Oh, similar to like, oh, you can find the length. Oh.
Yeah, so the radius is the length. So I know that if we're converging from 3 to 7, I know we also have to converge below. Maybe not at that endpoint, though. So I know we're going to converge down to -1, but we don't know what's exactly going to happen at that endpoint. I know at least up to that, though, it'll converge. It's got to be symmetric. In fact, if you're clever, you could probably deduce that it will converge at this -1. That since it converges at the right endpoint, you can show that it'll probably converge at this left endpoint by a clever alternating series argument.
Wait, I have a quick question.
Yeah.
How would you prove x equals 0?
Where's x equals 0?
In between -1 and 3.
Yeah.
But how do you know, unless you minus 4 on the 3, and that's how you get -1. But I'm not too sure how you know from -1 to 3 that it's also convergent.
So if you want to get into the technicals a little bit, I know we converge at 7. So that's Cn 7 minus 3 to the n converges, meaning this sequence converges. In other words, if it converges, we know it has to pass the divergence test. That these terms go to 0, which in some sense is going to tell us that Cn has to be less than 1 over 4 to the n for large enough n. It might start bigger than this, but we know at least the rate of decay of Cn has to decay faster or equal to, or at least on a similar order of 1 over 4 to the n. Because otherwise, if it didn't decay faster than this, the 4 to the n would outgrow the rate of decay of Cn. So if Cn is less than 1 over 4 to the n, and we want to check something like x equals 0, of course, we got an alternating part in there, but we could even ignore that alternating part because I know that Cn as an order of decay, it's going to grow like 1 over 4 to the n, if not decay even faster. It's going to get smaller even faster than this sequence. So we know that's in absolute value. This inequality will hold up to a large enough n. And that's just a decaying geometric series. And so we know this converges. So this is going to have to converge.
Oh, so you don't even use the timeline, you would just reason through it, I guess is a better way to put it.
Yep, you can do it that
Okay.
way as well.
Would you have to, I guess, would you have to do it this way on like the exam, or could you just say it?
I think you could just make arguments about the radius of convergence. You can say that the center of the power series is at x equals 3. So you could just essentially write out what we drew here. You could say that the center of the power series is at x equals 3. And because we know it converges at 7, we know that the radius of convergence is at least 4.
Right.
Meaning that the interval of convergence is at least bigger than -1 to 7. So we do know that the radius of convergence, it is a radius. It's a symmetric on both sides. This is a one-dimensional circle, is an interval. So from 3, we go to the right by that radius, at least 4, which means we can also go to the left 4. And all of those values within there are going to be convergent for the power series.
That's what I was thinking, like it's technically 4 to the left and 4 to the right. And then that's what I noticed. And then the 10 is because of like if you plus 3 on both sides, then you get 7 to 10. And if you minus 3 on both sides, you get negative. Okay.
So that blue is our converge. We know for sure converging by the interval of convergence. You could also do a ratio test, actually, if you wanted. Since we obtain, you can essentially do a ratio test to deduce this kind of information. We know that the ratio of Cn over Cn plus 1 is going to be at least 4 when we compute that limit. So this area, they should have modified this problem, actually, because this area we don't know. Could converge or diverge, and then exactly at 10, we know it starts to diverge. So if they give you a question like, will it converge or diverge at x equals 8?
Then you
We
say
can't.
inconclusive.
Yeah, we can't tell.
So if it's in between like converge and diverge, then it's inconclusive.
Yeah.
Okay, but okay, that makes sense. Okay.
I feel like couldn't you just plug in x equals 3 into the equation?
Yeah, what'd you get if you do that, though?
You just get, or I guess I do x equals 4.
Yeah.
'Cause then I just get 1 to the n.
Yep.
And anything to the 1.
That's how you do part B.
Okay.
Part B, you can say the sum of
That
c to
makes
the n
sense.
is just the power series evaluated when x equals 4. And we know that x equals 4 is in our convergence zone. So we know.
Okay.
I think that's all the questions I had for today. Okay. Well, thank you so much. I hope you enjoy the rest of your weekend.
Sure. Thanks.
Oh, I need a little bit of help on 5a. So I ended up getting to the sum of x to the n plus the sum of x to the n plus 1.
Yeah.
I'm not exactly sure where I can go from there.
We talked about this one in class. This one's a little weird, and it's kind of like comes down to like a philosophical issue of what is the nicest form of a power series. Again, like we've kind of been seeing these questions a lot all semester of what does simplified mean? Of course, everyone starts asking, even in pre-calc, what is simplified enough? And it only gets to be a harder question to ask, especially when we have things like this. What is a simplified power series? What is the nicest power series? We can actually combine these into one sum almost. So I'll put one in parentheses, one in brackets. So in parentheses, what do we have? 1 plus x squared plus x cubed plus all the way up to infinity. And then the next one, we have same thing, except we start at x plus x squared plus x cubed, and then of course all the way up to infinity. So we could combine all the terms. And now we could try to write it as a series. This is why all this algebra practice, it comes up again and again. Finding closed form expressions is important, even now again in series. Sorry about my phone here. The problem is what's the sequence of coefficients with this guy? It doesn't follow a nice sequence until after the 0th term. Nice sequence, 2, 2, 2, 2, 2. That's an easy sequence. But what do we do with that 1 is kind
Would
of
you
the
just
question.
switch it to n equals 1 and just kind of take that term out?
It's essentially what you got to do. If you're going around, if you're going this route, you kind of have to leave that 1 out and then just write it as 2x to the n. You can start at n equals 1. And so then there's kind of like a, the philosophical question of what is a power series, and is this a power series? It's a sum. We have a nice closed form sum, but then I have this extra term hanging off. Does that count as a power series? Well, what if I have 2 or 3 terms hanging off? Does that still count a power series? And this actually comes up again in differential equations. Once you start to use power series to solve differential equations, it takes things to a whole extra level when you're trying to finagle and combine different power series with different indices and try to come up with nice closed form expressions for the sequence of individual terms. Sometimes you can, sometimes you can't. So this is about as nice as we can get it if we go this route. I mentioned this in class, and there's another way to do this problem if we change the center of the power series. So this is centered at 0. If you take 1 plus x over 1 minus x and recenter it, the problem is this multiple of 1 plus x. Because one of the terms has an x, which is easy enough to multiply our power series by. Of course, so is the 1. But because of this index shifting, it doesn't make for a nice and concise way to combine all of the constants. Most of the constants, most of the coefficients combine nicely. But if we could recenter the power series at -1 for this guy, then this product would work out pretty nicely. So let's actually write it as x plus 1, since usually we have an x minus a for our center. And then write this guy here. What we want to do is force an x plus 1 here. But if I have a -x minus 1, we have to add an extra 1 on the outside to make those two terms the same. But now what we can do is factor out that 2 from the denominator. And write it something like that. This camera doesn't seem to want to focus. There it goes. It looks a little clearer. I think the lighting changes as the sun is kind of setting. The lighting here changes, and it affects the focus a little bit. But now we can write a power series, and look where the center of this power series is. It's already at x plus 1 over 2, and then we've got this extra x plus 1 over 2 term. And so this will combine quite nicely to get a nice and concise closed form series without any extra terms hanging out.
So pretty much your goal in this, like, problem was to, I guess, have the whatever's inside the sum and whatever's outside the sum like the same function.
In some sense, yeah.
Okay.
I'm not sure how strictly they're going to grade this one or really what they were looking for. And it's, again, it comes down to this philosophical notion of how simplified is simplified. What is the nicest form? Because in some books, this is nice enough. And usually working with the +1 isn't too hard if we have to leave off a constant term from a series. But I think in general, it's maybe argued that, this form, it's a little nicer, at least as it's written, even though the expression itself looks a little more complicated.
Okay. Well, on the exam, would you guys take the 1 plus the 2x to the n, or would you guys take the answer that the 1x plus 1 over 2 to the n plus 1?
That is a great question, and I do not know the answer to that.
Okay.
Because we haven't conferred with each other on grading and how these are graded. In my opinion, this wouldn't be wrong. You wouldn't lose all of the points for this. And I would think that you would get all, if not, it maybe a point off. But I think that method would probably be worth full credit.
Okay.
Since I don't know. I'd have to check with OCEDA and the graders. It's just like we haven't had too much time to go through this type of stuff, and this gets a little fancy. And so I don't know. I personally wouldn't expect you guys.
Yeah, because I felt like the second
rigorous.
method was a lot more complicated.
Yeah, like you got to be more clever. And with the limited time frame we've really had working with Power Series, I don't think we would expect that degree of knowledge and being able to manipulate Power Series quite yet. The Calc 2 level, this is a pretty good Calc 2 level in my book.
Okay. And I had one more question on 5b. So when you have the tangent to the -1 times x, because I see like the x after the fraction, doesn't the x on there and the x on the denominator cancel out? And then isn't it just arctangent of x?
Wait.
Or is there a different way to do it?
I think you're confusing something there. I think you're getting an extra x somewhere. You want to think of it as 1 over x times arctan.
Oh, because in the written homework, I think it's arctangent to the x over x times x.
For which one?
For 5b.
Yeah,
I don't know, there's an extra x hanging off the fraction. I don't know if that's a typo or not.
Do I? Unless I have the wrong file. So this is your homework 6.
Oh, that's a dx. Okay.
Oh, yeah.
Guys, yeah, it's typed wrong. All right, that makes sense. Because I was a bit confused because it just said x and it didn't have the integral.
I see. It might have been like a loading thing. Sometimes the integral and the special characters, depending on what kind of PDF editor and viewer, sometimes those things don't load properly.
Okay.
Ollie, sorry, I didn't see your question, but yeah, what you said in the chat, write your k to the 1 over k as e to the natural log of 1 over k times e to the natural log of k times 1 over k. Yeah, that'll work. It's a good way to take that limit.
And for this arctangent at x, do we have to show like all the deriving that we had to do during lecture today? Or can we just write the resulting sum down?
I would just quote it. Say it's in the book as well. There's a table of all of those integrals in the book. So just say we know the power series for arctangent from lecture, just so that the graders know. I might send them a note too.
Okay.
Yeah, typically if we've derived something in class, you can usually use it. I mean, because you're using the power series for 1 over 1 minus x on this homework. So you might as well, if we've done the power series for arctangent, you can just go ahead and use it.
Okay, and I guess what would happen to that factorial though? I'm a bit confused on where that would go. Would it just be considered like a constant? You just move it around, or would you?
Yeah. So it's an n factorial.
Oh wait,
do you get a factorial? Arctangent doesn't have a factorial.
No, it doesn't. I was looking at the sine and cosine one for some reason, but just out of curiosity.
But in general, if you're integrating these power series, all of the n terms aren't the variable you're integrating with respect to. So all you got to do is integrate the x terms. All of the cn's and 1 over n factorials, those are all constant relative to your integral. So you can just integrate term by term with the x's.
Oh, okay.
For the alternating series test, if we prove that it's convergent, are we able to say it's absolutely convergent, or would we have to do another test?
For an alternating series? What do you mean?
Yeah.
Like a general alternating series?
Yeah, I guess so.
So general alternating series, like if you pass the alternating series test, then it will converge, but you don't know if it converges absolutely. Meaning that if you take the absolute value of individual terms, you don't know if that will converge. You have to do an extra test for that one.
What exactly would be that test? Like
then you would want to do either like a ratio test. Actually, if you're going to do a ratio test is a strong test. So if a series passes the ratio test, it will converge absolutely. You don't even have to do an alternating series test. But like, for example, if you just have a generic problem of something like Bn is a sequence with the limit going to 0, and it's decreasing, then we know that if we make it alternating, say Bn is a sequence with decreasing also bigger than 0, we know that this will converge by the alternating series. But we don't know what's going to happen if I don't make it alternating. We would have to use a specific sequence and know what the Bn, what the sequence of individual terms is doing. We would need to know whether it's, if it looks like a polynomial, we would want to use a p-test. If it looks geometric, we could use a ratio test. We would need to know more. So for example, you could check Bn 1 over n squared, and then even more exotic things like 3n minus 2 over 2n plus 4 to the n. Any of those types of things. 1 over n natural log of n is a good one. Things like 1 over n to the 1 plus 1 over n. That one's a hard one to do. And all of these, each different, depending on what the sequence actually is, you would have to do a different test to see if it will converge absolutely.
Right, yeah.
But all of these, except this one's terms are going to go to infinity, or at least be too large. These ones, we know at least the terms will go to 0 individually. And so they will be alternating. They will converge in alternating series. However, if I take away the alternating part, now you got to do different tests to determine if those series would converge.
Yeah. Okay.
I'm a little confused on number 3. Like, I kind of just don't even know like where to start with that one.
Radius and interval of convergence. So first thing is you want to be able to write out a nicer expression for the sequence of individual terms. Two times 9, that one's a little weird. Plus x plus 4 cubed over 3 times 27. I wonder if that's a typo. I think that is a typo. Otherwise,
Yeah,
it doesn't
'cause
make
I think that was what was messing me up.
sense. This should be a 3.
Okay.
So our Cn looks like 1/3. 1 over 3 times 9. 1 over 3 times 27. So what is our sequence there?
It kind of looks like it's 3 times 3 to the n.
Actually, 1 second. It still isn't right. Unless there's another term. Yeah, this doesn't work. I'm not sure if that should be a 3 or if there should be a 3 here as well. Because then you have 3, 9, 27, and then these individual 3s, or if perhaps the sequence is 1, 3, 1 over 2 times 9, 1 over 3 times 27. I don't know if it would go back to a 2 times 81. What is going on with that? Oh, I see. Never mind. Okay, it's not a typo. This happens with series sequences. Let's write it like this. X plus 4 over, we'll write it as 1 times 3 plus x plus 4 squared 2 times 9 plus x plus 4 cubed 3 times 27. That is the pattern we're looking for. I wish they would have given us one more term. If they would have given the 4th term, it would have been easier to see. Usually, if you're writing it out and you want people to recognize a pattern, 4 terms is pretty standard. Sometimes it's hard to see a pattern from just 3. So the next term is, of course, x plus 4 times 81. And so now, what is our CN? We'll start at n equals 1 to make things easier for ourselves.
Would the denominator be something like n multiplied by 3 to the power of n?
Yep. So when we want to compute our radius of convergence, the sequence of consecutive terms, the ratio of consecutive terms to be less than 1. In other words, we get this guy. And so now we just need to compute that limit.
Why are you constantly writing down that absolute x plus 4 is smaller than the limit?
So the absolute value of x plus 4 is what is going to give us the interval of convergence. This limit gives us the radius.
Right.
But the interval is going to be centered at -4. And so that operation is dictated by that absolute value.
I'm a bit confused. You wrote that initially it would be Cn plus 1 over Cn,
Yep.
and then you wrote it changed to like Cn over Cn plus 1.
Yeah, since we're multiplying that over, multiply the Cn over, divide by
Right.
the Cn plus 1.
Mm-hmm. Yeah. Oh, and that's where you got X. Okay, that makes sense. Yeah, my bad.
Would the radius, like the limit of that, be 3, or did I make a mistake?
Nope. Limit is 3.
So I'm a bit confused on this part. So yeah, I ended up getting 3. Would that be your radius of convergence, or would you have to add that, or well, in this case, subtract that 4 onto that 3?
The 3 is your radius.
Okay.
The interval of convergence is here at -4, and then you would add 3 to both sides.
Okay.
So if we add 3, we'd be up at -1 to -7. So
Okay.
this whole space is the interval. But then this distance.
Wait, just the 3 is the radius. Okay,
Yeah.
that makes sense.
This distance is the radius.
All right. Yeah, that's all the questions I have. Thank you so much.
Welcome.
Thank you on that one. And I just have like one last quick question, if you don't mind.
Sure.
For 2C, I tried to do the root test and I got 1, and I just like that, so that clearly wasn't like the right one to use.
Right.
So
That was.
real confused which one.
I was thinking about that, and I was kind of waiting if anyone would work it out. Let's just see.
I was about to ask the same thing. Yeah.
Because a root test with a 1 is inconclusive, so maybe we do have to do the ratio tests. Let me see if we can find the work for that guy somewhere, wherever we were working out. Here it is. Yeah, so unfortunately, when you compute this limit, you got to do some fancy logs and stuff. This one goes to 0. Actually, no, this should work out because of this pi out front. You should get pi times 1.
I was talking about 2C, not
2C. Am I looking at a different one?
Yeah. And so I was just wondering, like,
that one.
yeah, if there's like what route I should try next.
That one should definitely be a root test because you're taking the nth root over m plus 1. Yeah, you shouldn't get, I don't think you get 1, do you? Because that's going to simplify to m over m plus 1 to the m. And so what you want to do, if you compute this limit, it's going to be 1 to the infinity. You can get around some of the work for it by just finagling it. So if I factor out an m, you can get 1 over 1 plus 1 over m to the m. Oh, never mind. That's not going to work. Sometimes you can get e's out of expressions like this, but it's a rational one.
It's definitely tough. Yeah. I got stuck on this one.
So then you got to compute this limit, which you probably have to do your finagling. So let's keep it as m over m plus 1. We'll take a natural log so we can pull down that m. We got to remember to undo that natural log. And then we want to compute the limit of this guy. So we want to compute the limit as m goes to infinity of natural log m over m plus 1 over 1 over m. Is this what you guys did?
I didn't think about
So in this
taking
case, that'll give us a 0 over 0. So now we can do L'Hopital's rule. Because the problem here when we compute the limit is it's going to go to 1 to the infinity, which is an indeterminate form.
Yeah, that's where I got stuck. Not that it equaled 1. I just got mixed up. So yeah.
So indeterminate form, 1 to the infinity, you have to do this natural log trick where you call the limit L for whatever that limit is, then take the natural log of both sides. We should still have a limit over here. Now, once we compute the limit, then we can undo the natural log by exponentiation. This limit is going to be messy, though. Because you're going to have 1 over m plus 1. Then you've got times that derivative, which is going to be a quotient rule. And then divided by this guy, which will give us a negative 1 over m squared. So just mind the algebra. It actually may not be too bad. Take the reciprocal of that term, multiply that m up, simplify that numerator, and then compute the, from there you should be able to compute a limit once you do all the algebraic simplification, because then it'll just be a basic rational expression.
Okay, thank you so much.
Where'd you get the m plus 1 minus m over m plus 1 squared?
That's the quotient rule, right?
Right.
Natural log is chain rule or quotient rule within the chain rule. So we take the derivative of natural log 1 over the argument times the derivative of the argument is that. That's our quotient rule.
So you're multiplying them by each other? Yeah.
Yep.
Oh, okay. Right.
All right, I got to get going. Happy Friday. I hope this was helpful. Hopefully you guys got not much more work to do on this.
Yeah, thank you.
Thank you so much.